Let me start recording. Yeah, I have a YouTube channel. So I'm going to plan. I'm planning to upload your talk, but don't be stressed about that. sorry, but if your talk is not nice, then I'm not going to upload it.
Let me see if this works better. So every time I go full screen, it stops sharing. Let me see if now it's better. Okay, now I think you see me change slides, right?
Yes, I can see. Yeah. Okay. I think that we have some people. I think the more or less we have a good people here. And I don't expect many people to come. But I think that hopefully we have a nice discussion. So let me first introduce Eric Kuflik to everyone. I think that Eric Kuflik is my collaborator. We worked together on strongly interacting massive particle before, and also unit Hofsberg in the same university. So Eric, I think I met Eric back in 2015 in a GGI workshop, and also I think before we was met. It was the first time that we met in GGI, or
I think so.
Yeah, I think that we also met in KIAS, right? Also another time in GGI, and Eric did his PhD in the University of Michigan and Harvard under the supervision of Professor Gordon Kane in 2011, and he started his postdoc position in Tel Aviv University in Israel, and he also continued his career in Cornell University, and he started. I think that he moved to Hebrew University of Israel, Jerusalem in Israel, from 2017. So I think that Eric is very active in BSM phenomenology. In particular, he proposed many interesting ideas for dark matter. So I'm looking forward to his nice talk and good discussion.
Okay, great. Thank you so much. Thanks for the introduction, Yamin. I think the first time we met was at GGI, I think. So please feel free to ask me questions during the talk. Any more details that you want. It's easy since I can open up my iPad and answer questions. Also, if you want to do more detailed calculations. So today I'll tell you about super heavy thermal dark matter. It's something I've been working on now for a few years. They say not to talk about not talk about two things during talks. So I'm going to talk to you about three things. These are three papers that I've worked on, three different types of works. I worked with the different collaborators on the ways to get heavy thermal dark matter out of early universe cosmology. And so the question is why? So why am I interested in going to heavy thermal dark matter? And so before that, let's start with what's been going on in the past 40 years. And we all know that the star of the show for what dark matter might be has been the WIMP, the glorious WIMP. Also, axions have been a very big topic, but I'm not going to talk about that. And so, why has the WIMP been such an amazing dark matter candidate? So, imagine you have some dark matter annihilation to two standard model particles in the early universe, and we parameterize this cross section as some coupling squared over mass squared. And we go ahead and we solve the Boltzmann equations. We solve the evolution for it in the hot thermal Big Bang. I'm hearing like a little bit of an echo. Okay, let me try again. Okay, now it's gone. And so you'd find that you'd get the right abundance of dark matter if the mass goes roughly like the coupling times 30 TeV. And so what we find, if you plug in, let's say, we'll be coupling alpha around 1/20, 1/30, then you get masses of order TeV, the weak scale emerges. And this is called the weakly interacting massive particle, or the WIMP miracle. And it's easy to see why we love it so much is because it's very simple and it's very predictive. And the reason why it's so simple and predictive is because it's a thermal relic. Because in the early universe, this interaction, dark matter goes standard model, is going very fast back and forth. And this keeps the dark matter in equilibrium with the bath. So its abundance is just determined by the temperature of the system. So it's completely insensitive to any initial conditions. It doesn't matter how much dark matter was produced after inflationary reheating. It doesn't matter what other interactions it has. It doesn't matter anything else. Its abundance is set by an equilibrium distribution. And so the dark matter density is evolving as the universe expands and cools. And it's an equilibrium early on. At some point, the temperature reaches to roughly where the mass is of the particle. And its density stays in equilibrium. It's becoming Boltzmann suppressed because it's non-relativistic. And at some point, it departs from equilibrium. And all the physics that determines the abundance right now is just determined by this point in which it turns where it falls out of equilibrium. And so like, again, I want to make the point that it doesn't really matter at all what happened before this point because it was in equilibrium. What matters is its departure from equilibrium. So much so that you can just calculate the abundance today by using the so-called instantaneous freezeout approximation, where we'll just calculate at what point is the rate of scattering, at what point does dark matter find itself and scatter, what point is that equal to roughly the Hubble scale, and that tells you the density over here when it departs from equilibrium. And so you can essentially get a very good estimate of the relative abundance by just calculating what is the density of dark matter when it stops annihilating. And I want to say furthermore, this idea of just determining the abundance of particles now and the physics of particles now from the Big Bang, just determine them from the properties when they're going out of equilibrium is something that we've done quite a bit and something that's been basically a guiding principle in all of cosmology. For instance, we determined the abundance of the light elements from Big Bang nucleosynthesis. They were in equilibrium at some point. The temperature comes to low roughly around MeV when the binding energy of the nuclei starts to become significant. And you can determine, for instance, the abundance of helium and deuterium just from the departure from equilibrium. This is what we do at BBN. The same exact thing we can calculate from the hydrogen recombination. What temperature is the C and B decouple? What are the free electron fraction in the universe? And we make very strong predictions from here. So I want to stick to this very simple guiding principle of cosmology in which you have a particle that's in equilibrium. So it's not sensitive to initial conditions, and then it goes out of equilibrium, and you determine its abundance right now from its departure from equilibrium. And one more thing I want to add that I forgot to say is that not only is this principle, but the abundance of the WIMP, for instance, is determined by how it couples to the standard model bath. And so predicting its abundance also tells you how you might discover it, okay? Because this freeze out, this annihilation gives you a direct coupling to the standard model bath. And so I'm sure you've seen this type of slide before. So you've been searching for WIMPs for the past 40 years, and there's like this amazing program. We've looked for dark matter direct production in, for instance, at the LHC, where we smash standard model particles together and hope to get dark matter particles out. We've looked through direct detection experiments in which you have some big pool of stuff. In this case, it's xenon atoms, and you look for dark matter coming in. It interacts with the material, and you look for those interactions. And then we also look to the sky, where we look for some standard model remnants like photons or antiprotons or protons or electrons coming from dark matter annihilations or decays in the sky. So these experiments are all getting increasingly sensitive. They're probing an incredible amount of parameter space, and there's still a lot more work to do in the WIMP program, but we still haven't found it. And so I would say that the status in 2021, or maybe even for a couple of years now, is a dominant paradigm for what dark matter be might be is being challenged. And so I think now this is a really great opportunity for new ideas for what dark matter can be, and use these new theoretical ideas to tell us how we should look at them experimentally. Because if you really think about it, the WIMP mass scale is just a very, very small range of total mass scale of what the dark matter might be. It can be some 30 orders of magnitude below the WIMP scale or some 50 orders of magnitude above the WIMP scale. And so I'm going to point to you now some few interesting scales, which are some guiding principles for where we might look for dark matter and why maybe we should look beyond these scales. So the first is so-called warm dark matter bound, roughly around the keV, in which dark matter would be warm and strange structure for formation. So thermal dark matter typically thought to be above 10 to the minus 6 GeV because of the effects on structure. Another bound is around an MEV, in which you think that naively a particle that's in thermal equilibrium with the bath at the time of Big Bang nucleosynthesis and relativistic would change the predictions of BBN. And so this turns around roughly a lower bound of dark matter mass around an MEV. And the final one, which I'll focus a lot on this seminar, is called thermal unitarity limit, in which it's roughly thought that dark matter above this mass would never efficiently annihilate away to get the right abundance. And I'll explain this in more detail. And so what I'm going to show to you today is that a thermal dark matter particle with all the wonderful same properties of the WIMP, just as predictive, just as insensitive to initial conditions, and its abundance determined by close to the standard model, can be in this entire range from, let's say, 10 to the minus 6 GeV all the way up to the Planck scale. And so there's been a lot of work on light dark matter, including from me and from you guys, but I'm not going to focus on that in this talk, but this is very fascinating work. What I will focus on in this talk is this so-called super heavy dark matter beyond what's currently thought to be the unitarity bounds. All right, so let's get into super heavy dark matter. Before I do that, are there any questions on the introduction?
I think it is clear for me.
Okay, great. Okay. So let's understand this so-called unitarity bound. Okay, so back to the WIMP calculation. So you have some dark matter that annihilates in the standard model. You parameterize its cross-section by some coupling squared over mass squared. And you find that you get the correct abundance of dark matter for the mass goes like the coupling times 30 TeV. And so if I look at just perturbative couplings, what's the largest coupling that I might put into this? Let's say 4 pi. You plug that in and you find the dark matter mass is going to be on 300 TeV. So this is the so-called unitarity bound. This is just saying that for perturbative interactions, you'll never find the dark matter mass greater than around 300 TeV. You could be a little more fancy and do some partial wave unitarity expansion. This is what Grice and Kamikaze originally did, but this is roughly the answer. And so let's try to understand it a little more physically. And so what exactly is happening? So recall this is the amount of dark matter in the universe, okay? And it's an equilibrium at early times. This thing here is the equilibrium distribution, and it's coming down relativistic, so it's becoming exponentially suppressed, and it's going to freeze out. So for larger cross sections, it can stay in equilibrium longer and have a smaller number of dark matter. But for smaller cross sections, it will decouple from equilibrium earlier and have a larger abundance. Okay, so if there's a larger cross section, the dark matter annihilates away more. So there are fewer dark matter particles. But what we know right now is dark matter energy density, not the dark matter number density. So if there is fewer dark matter particles in the universe, and we know that the energy of each particle is just its mass, and we know its energy density, so if there are fewer dark matter particles, then the dark matter particles must be heavier to make up for the energy density. And so if you annihilate away more, then dark matter needs to be heavier. And so you'll just find that given the unitarity bound on cross sections, you'll never deplete it enough to predict heavier dark matter. And this is the unitarity bound. And so there have been a lot of papers going to heavy dark matter, but they're all sort of kind of non-thermal. So there have been ideas to use non-thermal effects to get heavy dark matter, have it a result of inflationary production. Maybe there's some sort of late reheating or some depletion of the dark matter density. Maybe it's produced gravitationally, or there's some other non-standard cosmology. And I've worked on these ideas, and I think they're super exciting. But what I think that they're lacking is that since they're non-thermal, they're often very sensitive to initial conditions, and the abundance of these particles is not always related to how it coupled to the bath, and so it loses its predictivity in the sense that, I calculate the abundance, that tells me its interaction with the standard model, and that tells me how to discover it. And so what I'm going to show to you now in the rest of this talk is how with these three simple scenarios, how we go beyond unitarity while keeping the thermal scenario, while keeping the insensitivity to initial conditions, and while still having the relative abundance determined by its couplings to the standard model. Okay. Because just to start the simple argument, let's compare these processes. So here is this WIMP type process I've spoken to you about so far. So what happens here is two dark matter particles annihilate to two things, thing one and thing two. Okay? So the rate at which dark matter annihilates, so dark matter needs to find a dark matter particle to annihilate, so the rate is proportional to the number density, times the cross-section in which this annihilation takes place. And so this is happening when the dark matter is non-relativistic. And so the density of dark matter is very, very low. It's very rare. It's very hard for the dark matter particle to find another dark matter particle. So this rate is Boltzmann suppressed. So as it's annihilating away, this rate falls off exponentially fast. So it's not a very efficient way to deplete dark matter. And so what if instead of dark matter annihilating off itself, it's annihilating off a light particle, an abundant light particle? So remember, light particles are not Boltzmann suppressed. Their density goes like the temperature cubed, not like E to the minus m over t. So dark matter to annihilate into two other things, doesn't matter what they are, it needs to find a light particle. So that's very abundant times its cross-section. And so this rate here potentially can be very, very large compared to this sort of WIMP type rate that we have over here. And so if dark matter is annihilating off a light particle, then this rate for annihilation can be very, very efficient. And this is the basic idea that I'm going to use to show you how we can go well beyond the unitarity bound. Okay, is this part clear? Okay. So the first example I'm going to tell you about is called zombies. And I should say that my favorite zombie movies are the Korean zombie movies. I don't know why, but they're really good. And so let's consider this process first. So where dark matter annihilates off a particle called zeta and goes into two zetas. Okay, and we'll assume zeta is lighter than dark matter, so this process is going to be efficient. I'm calling it a zombie process because essentially what happens is that a zombie particle finds a dark matter, it bites it, and turns it into another zombie particle. And this is kind of, if you want, pandemic. And so this dark matter particle finds a zombie, or zombie finds a dark matter particle and converts it into a zombie. Some of the dark matter will survive until now. It survives the pandemic, it's hiding, or it just becomes rare enough that zombies can't find it. And eventually the zombies will just decay away, ending this dark matter zombie pandemic.
I have a question. Is zombie is dark matter candidate or something standard model particle?
So in the model, I'll have the zombie particle be another dark sector particle. So it's not the dark matter, but it's a particle that couples a lot to the dark matter. So the zombie is the thing that's depleting the dark matter. So it will be in thermal equilibrium with the bath in the model that I presented. But you can try to think about is whether or not the zombie can be a standard model particle. And so what should the masses of these particles be for this to work? Well, first, the dark matter should be heavier than the zombie. So this way, this is an efficient process. So the zombie is very abundant compared to the dark matter. You also don't want the zombie to be heavier than the dark matter because let's see what happens if it was. So remember, this is all happening when the dark matter is non-relativistic. And so the dark matter is converting to a particle heavier than it. It needs to fine kinetic energy in the bath. Where if it's non-relativistic, it has very small kinetic energy, and that becomes very, very unlikely to find a dark matter particle with enough kinetic energy to produce as a zombie. So dark matter should definitely be heavier than the zombie. And the dark matter should also be less than 3 times the zombie mass. Because if you look at this diagram, you can bring this zombie to the left to the right side of the diagram, and the dark matter would be unstable if it could decay into 3 zombies. So the dark matter mass should be less than the mass of 3 zombies. And so I've always wanted to do a numerical n-body simulation of something. So here I choose for the first time to do it of zombies. So here is my very fancy simulation of what happens in the universe during this zombie apocalypse. You see, here's your zombies, here's your dark matter particle, and you see at the end, mostly zombies, only a few of these fancy dark matter guys will survive. And you see he's pretty upset. He didn't really like this apocalypse. This is my very fancy first n-body simulation.
It's an n-body simulation. How many? How many?
No, I don't know. I think
it's
50 maybe. I think it's 50. And I have to admit, it's not really a simulation. I think I have them just randomly moving around and disappearing. But still proud of it. Okay, so now I'll get a little more technical. This is about as technical as I'm going to get during this talk. These next few slides. So if I lose you, you can decouple. You can recouple again in the next model, but also you can just feel free to ask me questions and I can elaborate. So there are 2 relevant processes: the so-called zombie process, dark matter in a zombie goes to 2 zombies, and the zombie equilibrium process that keeps the zombies in equilibrium with the bath. And so if you think about what symmetry stabilizes this type of process, well, think about it, the dark matter has charge 3 and the zombie has charge 1. So let's just come up with the U1 theory in which the dark matter has charge 3, the zombie has charge 1, and there's some scalar mediator that takes you between that mediates the zombie process. This is just coming from some sort of Yukawa coupling. And we'll gauge this U1 to be something like lepton number or E minus mu numbers, so that the zombies talk directly to the standard model through the U1 mediator. And there's also this other Yukawa coupling that couples the zombies to the Higgs and the lepton number, which eventually will be responsible for decaying the zombies away. I actually don't really use these couplings so much. I'm just going to keep it simple and parameterize this cross-section as some coupling squared over mass squared, and parameterize this cross-section as some coupling squared over mass squared. And I can determine these couplings from the model that I wrote down in terms of the gauge couplings and Yukawa couplings, but to simplify notation, I'm just going to parameterize them for now. And so you just need to solve these 2 Boltzmann equations for the density of the number of dark matter particles. So you basically have the change in the number density is one term coming from the expansion, from the dilution due to the expansion of space, and a rate in which 2 dark matter particles where a dark matter particle will destroy itself with a zombie, and the reverse process where a dark matter particle will be created by 2 zombies. And again, the similar process for the zombies in equilibrium with the standard model. And so there are 2 phases I want to talk to you about in this. So one is called the equilibrium phase, which is basically when the zombies freeze out after the dark matter, and the chemical phase in which the zombies don't freeze out after the dark matter. And you get different relationships for the relative size of the mass in terms of the coupling that produces the right relative abundance. And so let's first start with the equilibrium phase. Okay, so here's the equilibrium phase. So it's characterized by the fact that, so here is the density of the dark matter. Here's the density of the zombie. And so you see that the dark matter is freezing out before the zombies freeze out. Okay. So what does this mean? It means that when the dark matter is freezing out, the zombies are still depleting exponentially fast. Okay, so the zombies are reducing very quickly. And so this means that freeze out is going to be happening very fast because the rate at which dark matter zombie goes to zombie is going to deplete very quickly. And we can just use instantaneous freeze out approximation to calculate the abundance. And eventually the zombies freeze out. If you want, this is the so-called flattening of the curve, the end of the pandemic, and the dark matter is frozen. And so you can calculate the abundance here. Let's do it as an exercise. Just just schematically, so the rate at which dark matter is annihilating is proportional to the zombie density times the cross section of the zombie process. And then when that rate is equal to Hubble, that's when you approximately freeze out. That corresponds to this point here. And so you can solve this for the temperature at which you freeze out. You can relate the density of the dark matter to the density of the dark of the zombie. They're just given by the difference in the Boltzmann factor because they're both in equilibrium right before freeze out. And you redshift that value till now, and you calculate the dark matter mass that gives right abundance, and you find it goes like M, goes like the coupling square times mass to this R times the equality to 1 over 1 plus R. And so R is the ratio of dark matter mass to zombie mass, which is always greater than 1. So just to give some intuition, R equals 1 is what you would have found for the WIMP. So anything value with R greater than 1 will predict dark matter with mass much greater than the WIMP. So for instance, I take R equals 2, you have, so for WIMP, you would have M Planck times T equality to the 1/2. But for R equals 2, you have M Planck squared times T equality to the 1/3, which is a much larger number. Just in case you're not familiar, the Planck mass is 10 to the 18 GeV, and the temperature at matter radiation equality is in electron volts. Okay, so the more M Planck, the heavier the dark matter mass. And I'll plug in some numbers later to give you some better idea. So next is so-called chemical phase, and this phase is that when the dark matter is really freezing out and departing from equilibrium, the zombie has already been frozen in. Okay. And so what's important here is that the zombie, when the dark matter is freezing out, is roughly constant number density. The number of zombies is not changing anymore. So this means that the dark matter is annihilating on something that's very, very abundant. So this should give you even heavier dark matter in this phase. And so you can't really use instantaneous freeze approximation here. Look how slow, look how long it takes to go from departure from equilibrium all the way to freeze out. It takes a very long time. And if you want this so-called less flattening of the curve, maybe the zombies become an anti-masker, and this pandemic is not going to end. So it's very, very slow freeze out. And so you can do roughly find analytic answers for the relative abundance is, and if you want, you can read the appendix of the paper. But the important thing is that you find the dark matter mass goes like some coupling squared. It goes like the same formula that we had before, but there's an extra delta here, which is positive. And so more M Planck means heavier dark matter. And so you get even heavier dark matter for this chemical phase. And the physics reason is because the zombie is just so abundant when the dark matter is freezing out. Because it's so easy with dark matter to find a zombie and be converted into a zombie. So here is a phase diagram of all these different phases that we have. This might be hard. Okay, depending on if you're looking at it on your laptop, maybe you can't see the colors. So on the y-axis is basically the gauge coupling, how it's parameterized the interaction with the standard model. And on the x-axis is the zombie process. It depends on the Yukawa couplings. And so these blue curves here are curves of constant relative abundance, of constant mass. I get the right relative abundance. So here's 10 to the 4 GeV, 10 to the 6, 10 to the 8, 10 to the 9, 10 to the 14. And so this blue region here is the equilibrium phase. This green region here is the chemical phase. And you see that for dark matter around 10 to the 8 GeV, already well above the unitarity bound, you can find dark matter in both these phases. For 10 to the 9 GeV, you can find dark matter in the chemical phase. And even although I haven't described this phase here, you can find dark matter masses all the way up to 10 to the 14 GeV in this model. I'll just say what happens is that, as you've noticed, the zombie is always more abundant than the dark matter. And so the zombie can dominate the density of the universe, and the universe can enter a matter-dominated phase. The zombie will decay, it will reheat the bath, diluting the dark matter density, and you get the very heavy dark matter masses around 10 to the 14 GeV. I'm not really just pushing this thing right now because this really changes the cosmological history of the universe, so it goes against what I wanted to do. But still, in this simple model, you get dark matter masses only up to 10 to the 14 GeV. And so, key point, also we want to say the zombie was always more abundant than the dark matter, so it must decay away. And The problem is that the zombie is unstable, the dark matter is unstable. And so what you find is that dark matter is metastable. It'll be very long-lived, long enough to be dark matter, but it always will lead to a very nice indirect detection signal. So you can look for these dark matter decayings into 3 off-shell zombies, into whatever the zombie decays into, and you can look for those in the telescopes or satellites that we have. Okay, so to summarize zombies, in the thermal limit, we found in this type of simple model, you get dark matter masses up to 10 to 10 GeV and 4 orders of magnitude beyond the so-called unitarity bound. Still it's thermal, and still it's just as predictive as the WIMP. Okay, that's it for the zombies. Any questions on that?
So if you don't rely on the entropy production, so the dark matter mass is the maximum value.
Yeah, 10 to the 10. In this plot, it's 10 to the 9.
It's in
this
the
curve right here.
It's in the, you want to be in the, you're still in the chemical phase where the zombies are abundant, but still entropy dump is not important in that.
Right. This region here is where entropy dump becomes important.
I see.
And in this region here, the dark matter, the zombie freezes out while relativistic. So its abundance is always huge. So you get very large dark matter.
I had a couple of questions.
Yeah.
First, is your dark matter fermion or scalar, or both can be possible?
In this model, it's a fermion.
Fermion, and then maybe so you assign the gauge charge, I think mu minus L, mu minus E.
Yeah,
3.
I did E minus mu, or I could have done lepton number 2.
Mu. Yeah, then maybe chi decays into 3 leptons, like muons or electrons.
So you could have done a non-normalizable interaction, coupling chi to 3 electrons.
Yeah, maybe, but through loop.
Right. So you could. That would be let's say dimension 6 or higher. So depending on that size of the coupling, you would need that to be size of the suppression. You need that to be long enough lived for dark matter to be a dark matter.
What I was wondering is that if suppose it is dimension 6, then maybe dark matter must like cut scale or something, or is too heavy to be long lived, and it's the lifetime is too short. Simply. Is that, yeah.
So yes, I agree. If I had a dimension 6 R player, so that's a good point. So if I even specify the gut scale, the Planck scale, so if something like chi, no, it's not dimension 6 because it's dimension 6. It'd be like chi and a lepton, a right-handed lepton and two left-handed doublets, right? So that could, in this model here, it does decay into three leptons, but it's coming from a high dimensional operator because there's a Higgs bit in it. But that's true.
I see.
It definitely it is dimension 6, right?
Yeah, I think so. Nevertheless, like a coupling can be small. I don't know. It should be related to dark matter abundance. But
yeah, that's a good point.
Are you talking about the effective operator including neutrino? Because the chi is a charge neutral, right? So then do you have to consider SU to left-handed SU2 invariance for the dark matter, right? Because the neutrino is a doublet.
Yeah.
You can't couple to neutrino unless chi is the doublet.
Right, so it would be higher than dimension 6.
Right, I see.
Okay.
Yeah, I see. Thank you.
Actually, I think it is something the basic question. I'm sorry about that. Well, could I get what is the chemical phase?
So yeah. So chemical phase is just a statement. It's just a statement in which where this chi is depleting, where it departs equilibrium, the zombies have basically already frozen out. So the abundance is constant. Here, let me show both phases on the same plot for a second. So here you see that when the dark matter is freezing out, the zombies are still in equilibrium and they're depleting fast. Oops. Here you see that the zombies have already frozen out when the dark matter is depleting, and so if you want, it's called the chemical phase because the total number of zombies plus dark matters is not changing anymore. Right? No process is changing the dark matter plus zombies, right? Because the zombie process keeps the number of zombies plus dark matter constant. So that's what's called the chemical phase because they're in chemical equilibrium with each other during phase out, and there's chemical potential that's growing.
Ah, okay. Thank you. I got it.
So I have a question about this interesting new geometric average of the dark matter mass and temperature. And did you discover it? I mean, how did you discover it? I mean, did you make a certain ansatz to get heavy dark matter, and then you can infer what is the process producing the formula, or?
No, so in this case,
Yes.
in this case, all I do is do the instantaneous freeze-out approximation, calculate the temperature from this formula,
Yeah.
and that tells me the density of the dark matter at this place, and the rest is that to
Yeah,
equality.
I know the steps. That I remember I followed your paper in detail, but just for curiosity, because you are generalizing that kind of geometric average to these general processes. So I'm just wondering if you could imagine. I think I don't know if I can find another process.
A bigger power here,
or some generalization of you can make it to be more different value, like I don't know. Then
right?
you can look for the processes. I don't know.
Yeah, so you can think about that. So for instance, the WIMP is R equals 1, the SIMP is R equals 1/2. And so you want to make R as big as possible. I just think that for some cases you don't get this nice formula. For instance, in the next model, I don't know if I can write it in this way. It's more like an exponential, but we could see. You'll see the next model. You don't really get a relationship that looks like this. But
okay.
Yeah, it's right. So the goal is to get R as big as possible to get as heavy as dark matter. Then you just get the Planck mass.
Yeah, it is more predictive formula. Yeah, so just in terms of the single parameter. Yeah.
Okay, so the next example is this chain. Example, which I did with Youngjin. And so basically the example here, you have n dark matter particles, chi1, chi2, chi3, chi4, chi to chi-n, and they interact nearest neighbors through a chain. So they're all roughly the same mass, and chi1 can convert to chi2 and back and forth through scattering off the path. Chi2 can go to chi3 scattering off the path, and so on. And this is a very efficient process because we're going to take these standard model particles to be very light, so very, very abundant. So it's a very efficient process. And so also what we need is the last particles in the chain to decay in equilibrium. Because if you look at this again, the chain process doesn't change the total number of chi particles. It only converts them. So you need something that depletes the total number of chi's, and we'll see that the last chi decays in standard model and decays very fast. So it's in chemical equilibrium. So why do we consider a chain here and not just this simple 2-particle case? Is because, again, it's this fact that the dark matter would be unstable. So it moves the standard model particle to the side, and you'll find that one dark matter particle will decay into 4 standard model particles, and the dark matter will be just way too unstable for this to work. And so this is why we consider it a chain, because the chain makes the dark matter decay to an off-shell, have to go through each off-shell state. So Chi1 will go to 2 standard model particles, and an off-shell Chi2 to off-shell Chi3, all the way to off-shell Chi-n, and you end up decaying into 2n standard model particles, and this has a tiny, tiny phase space that goes roughly like 1/2n factorial. And so this makes the dark matter long-lived, the chain, long enough to be dark matter. And so how do we solve this abundance? And so let's first consider the 2-chain first. And so here you just need to solve the simple Boltzmann equation for the number of 1 particles. So the number of 1 particles is depleted by the chain going to the right, the process going to the right, and it's added by the process going to the left. But we're assuming that the number of Chi2 particles are in equilibrium. And so we have a very simple Boltzmann equation to solve that just has an analytics, it just has an analytics solution. You can just plug this into Mathematica and it'll give you the answer. And if you solve for the relative abundance, you'll find that the coupling, that you find that the number density at infinity, so this is roughly the yield for people who know what the yield is, it goes like lambda minus 2 over square root of lambda, where lambda is the general density times the cross section over Hubble evaluated at the mass scale. So don't worry so much what the formula is, but just I'll plug in some numbers of what the mass might be and what the coupling might be. So if I parameterize the cross section as some, let's say 1 over mass squared, normal perturbative cross section, you find the dark matter mass is 6 times 10 to the 14 GeV in this simple case. So this produces super, super heavy dark matter in a very simple thermal process and directly from its coupling to the standard model. And so, okay, that was just the 1 chain. We need to do the n chain. So I can write down n coupled Boltzmann equations and try to solve them. And you can do that by maybe diagonalizing the system, finding the eigenvalues, and just solving this, or solving it to a numerical solver. But that's no fun. As physicists, you want to find new ways of solving problems. And so what we realize is that this is just a diffusion equation in which dark matter is kind of like this drunk thing walking across different flavors of dark matter, 1 to n. So on the left, there's a wall where it can't go any further to the left. And at the right, there's a cliff in which if it gets to Chi-n, it just decays in the standard model. And so we thought about calling this like drunk dark matter, but we decided not to at the end. And so you can just turn these n Boltzmann equations into a simple diffusion equation with a Dirichlet and Neumann boundary conditions on each wall. There's a diffusion coefficient, and you can just go ahead and solve this. And you'll find some sort of profile for the dark matter density when it freezes out. It's mostly Chi1. It's only a little bit Chi-n. Here's the cosine giving that distribution. And the number density is roughly given by the number density found for the 2-party case, but in which that lambda is replaced by the diffusion coefficient. And so here, I'll argue that the dark matter mass can go all the way up to the Planck scale in this model. I think in our model that we built, we only got to, let's say, like a little bit below the gut scale. But I think with a better model, we can go all the way up to the Planck scale. Okay, so that's the finish for me for the chain. There's a lot of more details going into the chain. And I'm happy to discuss that later or now if you guys want. But is there any questions on the chain before I go up into the final set of work? So Youngman, so if I'll show you this quickly, this formula here for the abundance here, it's a little harder here to get this into the form of the, this has a very strange, form for the final abundance in terms of the cross section. It's an exponential here, and so it's a little hard to get in terms of the m Planck t equality formula. But maybe we could do it if we tried.
Well, this is just out of my curiosity, but this is basically multiple scattering with the standard model. And this reminds me something like Landau-Migdal polymetric effect, which suppresses the cross section. It's basically depending on how much energy can be transferred between dark matter and standard model. But is there any such effect, or you think it's a sufficient amount of energy can be exchanged between those two sectors?
So, I mean, so if we're taking the dark matter to be roughly close, very, very close in mass, these particles. So in a sense that it happens at almost zero kinetic energy. And so I don't think there's any necessarily non-perturbative or fancy effects happening in the cross-section, except if maybe there's a light mediator, like you're suggesting. But I think if there's a light mediator, then you won't find this process as important, but you'll find just the inverse decay process, in which chi1 goes to the light mediator and the final state particle. So in that sense, it's not the scattering that matters anymore, but just the light mediator directly produced on shell.
So do you have any specific interaction in this blob you have in mind? Like just you assume some effective ablator? Or?
So we thought of a few different things. So one, you can think about this as a U1, where there's some mixing that allows you, that's a U1 that's broken, which allows you to basically move up in charge. Like this would be a charge 1, this would be charge 2, and charge 3, charge 4. What that really makes you think of is an SU2 force, which a W is basically the raising and lowering operator, which can take you from 1 to 2 to 3. So I think the most natural thing is imagining this to be an SU2, in which the W boson is of this SU2, hidden SU2, or maybe even like weak SU2 is moving you up above and below the chain. In the paper, we just took a simple scalar particle that we just wrote on a Yukawa coupling to center model, but I think a W boson, something like that, is the most natural.
I see. Seems you're having some huge dimensional representation assigned for dark matter.
Yes.
Is that right? Okay, I see. Yeah. Interesting. Thank you.
So
now I'll go.
Can I ask a question about the appearance of the exponential factor in the number density? So it looks like there's some exponential suppression, although it depending on this lambda, the ratio. Is it sensitive to this value, or can you get a natural? Can you get a naturally get right now dark matter abundance? I mean, my question is whether your result is sensitive to the choice of this small lambda parameter or not.
Yeah, so this lambda is roughly the cross section, and that's the whole point. It's extremely sensitive. And so the point of the cross section, so for normal WIMP, this will go like 1 over, say, this will go like 1 over lambda. But here, this goes like e to the minus square root of lambda. And so that's how you get such heavy masses, because it depletes so well. But yeah, it's exponentially sensitive to this value of lambda. So it doesn't naturally tell you heavy or light. It just tells you that it can be very heavy.
I see. It's kind of chain reaction. I mean, all of a sudden, as you turn on certain coupling between dark matter and standard model, because of the chain reaction, you are reducing dark matter abundance.
Sorry, I didn't understand. Can you say it one more time?
It's kind of chain reaction. I mean, you have a chi1, chi2, and then there are multi-component. Is a multi-component dark matter, or the chi1 is the only dark matter component in this case?
So what we really need to have is each one being a little heavier, because if they were all stable in the same mass, you would have them all decaying at different times in the universe. Some would decay now, some would decay during BBN, some during CMB, some early on, and that would be problematic. And so we imagine is that chi2 is a little heavier than chi1, chi3 is a little heavier than chi2, so eventually they all decay backwards into the chain after freezeout. So even though this is the profile from freezeout, what we imagine is that they all go back this way at some later time. They all decay back into Chi1.
I see.
Because, right, because
I see.
Because right, if I cut this off here, each particle closer to the decaying particle has a shorter lifetime than Chi1, and that can be problematic.
I see. Okay.
I have a simple question that is,
Yep.
if there is some guidance to how much, how big chain, how much chain big, I mean, yeah.
Sorry, can you say it again?
If there is something guidance to how much chain should be.
How much how large this should be?
I mean, how much n should be big.
Oh yeah, so n needs to be long enough to make dark matter long enough live to avoid the interdetection constraint. So n needs to be large enough so the lifetime is, let's say, greater than 10 to the 27 seconds. And so I have a plot in the paper I can show you, but for like 10 to the 10 GeV, I think n should be roughly around 5 or 6, but to get up to the Planck scale, n should be roughly around 40.
I got it.
Okay, so I'm doing my last thing now. I'll try to do it quickly so we don't go too much over. So okay, let me skip this. Okay, so let's consider this very simple theory. This is what we call squeeze out. So let's consider this very simple theory in which you have a simple SU3 strong force, a dark strong force, SU3 color with one flavor. Okay, so it's a very simple Lagrangian in which you have the gauge kinetic term and the quark mass and kinetic term. That's also considered as theory in the limit where the quark mass is much heavier than a confinement scale. And so this theory is an asymptotically free theory with a first order phase transition. And so, what are the states of this theory? So at low temperatures below the confinement scale, we have the mesons, the QQ bar states. When we couple this to the standard model, we expect these to be unstable. And we have the baryons, the QQQ states and QQ bar, the Q bar antibaryons, and we expect these to be something like stable dark matter. So our goal is to really calculate the relic density of these baryons. And so let's first start in the beginning. So in the early universe, while you're still in the deconfined phase, the temperature is way above the critical temperature. You have normal freeze out of the quarks, like a WIMP process. Dark matter, the QQ bar is in equilibrium with the gluons of the dark sector, and they freeze out and they annihilate away. And so if the dark matter was very heavy, above the unitarity bound, which is what I'm going to consider, then you would naively expect the dark matter to be too abundant because it couldn't annihilate away efficiently, because this is just a perturbative process. But however, it's not the end of the story, because the quarks and antiquarks are not the dark matter. What's the dark matter are the baryons. And so what we need to understand is, how do these quark and antiquarks pair up? How do they buddy to form mesons and baryons? Because just the baryons that form, that will end up being the dark matter. And so to understand this, we need to understand, what does the phase transition do? And so, okay, so basic story here is stage one is what I call freeze out, in which you have lots of quarks, and then a little number of quarks, and they deplete and they freeze out. And after they freeze out, the quark and antiquarks are too far apart to form baryons and mesons. You calculate the so-called cross section to bind up, and you find that they're just not close enough to bind. And so the universe, okay, now filled with these quark and antiquarks, they're diluting to the expansion, but at some point the universe cools to the point in which you hit the critical temperature, at which you start to nucleate bubbles of the deconfined phase. And so what happens is, at some point you cool down and start you bubbling, just like you boil water, and you start getting bubbles, in which inside these bubbles the dark QCD is in its confined phase, and outside is still in the deconfined phase. And there's some rate of nucleation. Roughly what you find is that the bubbles all nucleate at roughly the same size at some minimal critical radius, which they can bubble. But we're actually not going to end up using that. And so after the bubbles form, they start to expand because of the growth. There's some balance between the energy density and the surface energy density, but these bubbles they're going to grow and they're going to expand. And these two bubbles are going to meet with each other, kind of like, and they're going to form one big bubble. Think about soap bubbles. When two soap bubbles meet, they combine to form one big soap bubble. And so this is called coalescing. And so as the universe fills with these bubbles of the confined phase, they're going to grow. And they're going to meet, and they're going to coalesce. And you can calculate approximately what is the radius for coalescing fast. And you'll find that for bubbles greater than this critical radius, the bubbles coalesce too slowly. But below this critical radius, the bubbles coalesce very, very fast. And so at some point, the universe is basically going to be filled with just half full of bubbles of roughly this size, because these will make up the largest bubbles. But another way to look at it is when the universe is half filled with the confined phase, it's also half filled with the deconfined phase. And so instead of thinking about it now as having bubbles with some radius r1, the universe is half filled with pockets of deconfined phase of radius r1. So now let's think about it in this sense, in which I have bubbles nucleating, they coalesce into big bubbles, and they're going to form like nice spherical systems. But now think about it instead, now I have shrinking pockets of the confined phase. So all these quarks now are stuck in the confined phase. They're stuck inside these pockets, and they can't escape. These quarks, they can't go out of the pockets because they need to form something neutral to leave a pocket, like a meson or a baryon. And so they're stuck inside these pockets. And so these pockets are going to shrink. They're going to shrink. They're going to shrink. They're going to dense. And they're going to get dense enough to allow mesons and baryons to start forming in the pocket. And mesons and baryons, they can escape the pockets. And so we need to calculate how many baryons escape these shrinking pockets. And that's going to be the abundance of baryons. And so we did do some complicated calculations. I need to calculate, how fast do quarks and antiquarks form baryons? What are the binding energies? What's the pressure of the quarks exerting on the wall to slow it down? How fast does the wall speed? How fast is the stuff inside the stuff moving, and so forth? And what we find is that the wall is moving fairly slow enough so that the quarks and the mesons and the baryons, they form an equilibrium inside this pocket, meaning that the densities are all related to each other. And so if they're forming an equilibrium with each other, then the number of baryons is substantially smaller than the number of mesons, because the baryons are heavier. But also keep in mind that when the mesons form, they deplete, they decay right away. And so if a meson forms and decays, it's not just depleting the number of mesons in the pocket, it's depleting everything in the pocket, because everything's in equilibrium with each other. And so what you'll find is that the quarks are compressing slow enough to form an equilibrium distribution of quarks, mesons, and baryons. And what happens is that basically all the quarks are going into mesons, and mesons are decaying. And so essentially the squeezing is going to reduce every quark in the pocket and every antiquark, except if there's accidentally more quarks and antiquarks, or more antiquarks and quarks. So everything will be removed with the exception of a possible asymmetric component in each pocket. And we didn't assume an asymmetry in the universe. So these asymmetries are going to be accidental asymmetries, just because of the randomness of gathering these things in pockets. Sometimes you'll have more quarks, sometimes you'll have more antiquarks. And so roughly, there's normal Poisson statistics of the absolute value of the difference is roughly just square root of the number of quarks in the pockets. And since all we'll have is left over is the remaining asymmetric component of quarks and antiquarks, which will just form into baryons, all we need to do to determine the abundance in each pocket is just know the initial value of number of quarks in each pocket. And that we can determine just by the freezeout density we saw earlier and the average size of each pocket. And that's it. And that's exactly what we did. And so just a picture, you have the freezeout, the bubble nucleation, they grow, they coalesce. Now think about these as shrinking pockets in which you essentially squeeze out the baryons. And so here we show the parameter space of the confinement scale versus the quark mass over the confinement scale versus the confinement scale. And here is the curve of correct relative abundance with some errors. And here are contours of constant mass. And so you see roughly you get masses, in this case, of the squeeze out of 10 to the 4 to 10 to the 5 TeV, well beyond unitarity bound, in a very nice thermal simple model. Okay, so just to summarize everything, so there's been lots of activity for thermal dark matter, both sub-GeV and both well beyond unitarity bound. These involve different types of interactions, processes that have relative importance throughout the cosmological history, which leads to very nice ways that dark matter can form the abundance that we see. These are novel frameworks. Maybe you think of them as generic. They're simple theories like the SU3 with one flavor. So in terms of discovering these, I think the best way to discover these are via strong indirect detection signals, because these often lead to super heavy dark matter, often leads to non-stable dark matter. And I think there's still much more to do in this field, and I'm happy to collaborate and work on more. Thank you.
Okay, thank you. Thank you for your interesting talk. So do you have any questions?
I had a question about the squeeze out scenario. Maybe I missed something, but those mesons should decay, but to what they can decay, or is it it must be standard model, but
yeah, I was agnostic about how it happens, but just assuming it decays somehow is maybe we charge it under the standard model, and like maybe it's like an SU2 doublet, so it decays to the weak force or something like that.
I see. And also after the phase transition, for the baryons, can they still be annihilating because of the some finite size of geometrics, and they can just scatter with each other and annihilate into mesons? Can this happen?
The density is never big enough for this to really happen. The baryons never become dense enough to really start to annihilate again.
I see. All right. Thank you.
Excuse me. I have a question about the chain dark matter.
Yes.
Maybe I don't understand the elementary point, but how the degeneracy is important in your scenario?
So the degeneracy is important because, one, this should be the lightest one. First, it should be the lightest one, so it's the dark matter, or also decay into other ones. If chi2 is heavier than chi1, then this is happening when dark matter is non-relativistic. And so if chi2 is heavier, then you need to find energy in the bath to upscatter. And so that would actually slow down the process to be what we call a forbidden process. And so the mass needs to be less than the temperature at freezeout, or else this process should become, for forbidden, meaning require energy that become Boltzmann suppressed, and it wouldn't lead to heavy dark matter. If you weren't interested in heavier dark matter, then it could be a chi2 can be a little heavier. But because remember we're at temperatures below the mass of the dark matter, so this is temperature T, this is mass M. So if this mass is heavier than T greater than this mass, then it would be unlikely to find a particle to upscatter, unlikely to find enough energy to upscatter into chi2. So they need to be very close in mass.
Okay. And you might have explained about the embedding, explicit embedding of this kind of model. For example, which kind of interaction is required, or which kind of symmetry is required as a setup.
So I think the simplest thing is to consider that these have some increasing or decreasing charge with each thing. So I like to think about it as some scalar with charge 1. And all these things have different charge by charge 1. And so you just have scalar chi1, chi2, scalar chi2, chi3, and not any of the orthogonal ones because of charge conservation. perhaps I can also just show the paper, but imagine some Yukawa coupling, which is a scalar of charge 1, and let's say chi1, chi I has charge I. That's the simplest case. And so chi1, chi2 dagger has charge difference of 1, so you need some particle charge 1 to go between them. And so in a sense that you only get the nearest neighbor interactions. Or like we said earlier, maybe it's an SU2, where this is some really large multiplet of SU2, and the W boson takes you from the nearest neighbors.
Okay, in that case, the mass degeneracy is ensured by order 1 Yukawa coupling, or I don't know.
Yeah, by the mass degeneracy would be broken by the size of this coupling, I would say. And so it's technically natural, but I mean, it doesn't need to be that degenerate. Maybe like 5% or 1%, depending on how heavy that you're going to get. So 1% is a loop effect. Is totally fine if you think about it as tree level degenerate, and then loop mixing is okay.
I see. Okay, thank you.
So in the case of chain dark matter, the heavier component, they are in the thermal bath during the freeze out, right? In order for them to I mean, for chi1 changes chi2, and then chi2 changes chi3. So if chi2 decays too fast, then you don't have such a channel, right? Chain reactions. So then
Right.
my question is, the chi2 decays after freeze out?
No, so chi2 decays later on.
Later, yeah.
Or if you want, yeah, chi2 decays later on.
Mm.
If chi2 is a little heavier than chi1, and so it's, if you have this like reverse decay, I'm not, that might be able to be in equilibrium. I'm not sure.
I mean, my question is, the chi1 is the dark matter component, which is the most long-lived, and then it lives until now, and then chi2, chi3, in the end they decay, and then they will be converted to chi1, and then in the end you are summing up all the dark matter component,
right?
Coming from chi2, chi3, etc.
Well, I think so. If they were completely degenerate, then yes. So you'd have chi2 decaying down to the chain chi3. But I think I'm imagining chi1 being a little heavier than chi2, not enough that it affects freeze-out calculation, but enough that chi2 can decay to chi1 and 2 standard model particles. And so that can be very fast.
Okay, so I think that this decay rate, chi2 decaying into chi1, is not fast enough, so that you are not recreating chi1 back in the thermal bath. So chi decays much later after freeze out, right?
I mean, definitely decaying after freeze out is fine. Just decaying during freeze out.
During freeze out, you think it is still okay?
I don't see an issue right now, but I don't want to say yes for sure. I mean, it's the total number is still depleting because of this decay all the time.
Because I see. In the end, as soon as chi2 is produced, it annihilates, and then annihilate through the chain into chi-n, and then etc. Okay.
Right.
Yeah. Are there any more questions? I think that it's you have a same topic with a different models. So yeah, it's interesting. So Actually, I couldn't follow the details of the freeze out. Sorry, not freeze out, squeeze out mechanism.
Right.
Actually, there are many ingredients there. So the basic motivation is that the quarks and baryons, that they are different, and then even if yeah, so in the end, below the phase trend and below the the condensation scale, you can form mesons and baryons, and then you set the so the baryon is the dark matter, right?
Baryons are dark matter. So inside this pocket, the quarks are combining. So this pocket is the deconfined phase. We can still form mesons and baryons, bound states and deconfined phase. And so what's happening is squeezing these things together. So you start forming mesons, you start forming baryons, and so on. But the mesons quickly decay away, and the baryons never really have time to form. And so essentially what's happening is squeezing in, you're mostly getting just mesons. The mesons will decay away and stable. And so essentially the squeezing is reducing everything in the system. And baryons are really never getting a chance to form. However, because there's likely to be more quarks and antiquarks, or more antiquarks and quarks in the thing, you can only form a finite number of mesons, because mesons is a quark antiquark. So at some point you'll be left over with just quarks or just antiquarks. And these have to form baryons as it gets smaller and smaller, and those baryons or those antibaryons will just escape.
Okay, so you said that this inside the bubble is the deconfined phase?
The bubble is a deconfined phase, yeah.
It is deconfined phase. So the baryons are not formed yet, or?
Baryons and mesons can form in deconfined phase. They still can form as bound states. They just don't form. Yeah, there's nothing wrong with forming them in a deconfined phase. In the confined phase, they have to be there. They're just no quarks. But in the deconfined phase, you can have both the quarks, the mesons, and the baryons in the deconfined phase.
I see. Okay, I see. So they are equilibrium in a sense.
Right.
And then I see. That's what you meant. Okay, I see.
It's like BBN, in which you do have you do have protons, but you also do have protons with neutrons and bound states. You have both of them.
I see. I think, yeah, there should be more questions from different people.
Actually, there's something about this freezeout that I'm also not understanding. So your bubbles are getting bigger and bigger and bigger, and then your deconfined space will be all the space in the end, right?
Yes. Eventually, it'll be all confined phase at the end.
Everything will be confined in the end.
Yes.
Okay, I was getting the opposite idea.
Yeah, I think these gray corresponds to the confined phase that is nucleating, and they grow and grow and grow until they fill out almost everything. Like here, and essentially the remaining deconfined phase is shrinking and shrinking and shrinking, getting smaller and smaller, and everything is left in the confined phase.
Okay, I see. Thank you.
So then this the region of deconfinement stabilized, still they don't shrink anymore any further.
They shrink forever until it goes to zero. It just shrinks in and goes away. I don't have a final thought, but it shrinks in and goes away until there are just baryons sitting there. Maybe it shows here. It's like eventually the universe just looks like this, where the baryons are all, these are the baryons or a bunch of baryons or a bunch of antibaryons, and the universe is just in the confined phase.
So it's kind of filtered, kind of filtering mechanism. I don't know. So initially, you have baryon and quarks at the same time in the deconfined phase, and then they shrink. You shrink the region and squeeze it. Still, you are left over around this small region. The red dots are supposed to be in the deconfinement phase, right?
Well, the red dots are supposed to be the baryons. Sorry, the red dots are like the baryons and antibaryons. So the baryons are forming inside the deconfined pockets, but they escape. They can get through the wall because they're neutral objects and make it into the confined phase.
I see. Okay, I see.
It's like you're saying. It's like the filtered papers in which the wall doesn't let through everything. It only lets through the stuff that can make it through. So here, the quarks and antiquarks can't make it through the pocket. This is very different in QCD, in which a heavy quark can make it through the pocket because it can just pop out a light quark out of the vacuum, and and the light antiquark and quark out of the pocket to become neutral and go through the wall. But here we have no light quarks, and so it can't just pop out a quark antiquark out of the vacuum to become neutral and go through the wall.
I see. Okay. You need the filtering mechanism. It's not filtered. It's just you pass through the wall. Yeah. Okay. But you have a suppression mechanism because of strong annihilation between quarks in the deconfinement. In the deconfinement phase, because they are okay. I see. Okay, so are there more? I think Eric is very happy to discuss with you, unlike the other speakers. So if you have any question and if you have new ideas, you can tell him that we can work together.
Of course.
Yeah, actually, yeah. So you have a paper. By the way, you have a paper on the April Fool's Day, right?
No.
April Fool's Day, you have a paper.
No, I don't think so.
You didn't?
Not me.
It wasn't.
No, maybe my
not
papers.
From you?
No.
I thought that it's a zombie paper, so I thought that you are one of the authors.
No, it wasn't me.
No, you're not. Okay. Actually, I tried to follow your zombie paper with Sumin, my former student, and we wanted to find a better model for zombies. Actually, I had a draft, so I can show you that draft to you. So if you find it still interesting, then maybe we can work together. But there's some minimal model for zombie dark matter. But I don't know, for some reason we didn't continue because it was during the lockdown in this engineer area in France, and then the Sumin was in Switzerland. My student was in Switzerland, and then
right, yeah, definitely the pandemic has put a lot of papers on hold. In the beginning, I wanted to think about something like clockwork because it looks like clockwork in some sense, but yeah, I'm very curious to see what you guys have done.
Okay. So also, chain dark matter. I think that there should be model building issues. So I think that it'll be interesting to think about concrete models in more details. Okay. And also, I think maybe I have a small comment about a question about the heavy dark matter in general. So here, I think you discussed a series of interesting possibilities. for heavy dark matter, which was once in thermal equilibrium with the standard model particles. And then if dark matter is so heavy, how to detect them? That is the maybe question, how to probe them. And then is there any alternative way to probe them instead of direct detection or something like that in general?
Right. So I think if there's a light mediator, maybe there's direct detection. If you have some long range force, maybe you can do direct detection. I think like maybe Maxime Pospelov and Joe Bramante and someone else had a paper about looking for multiple dark matter scatters in direct detection. So if it's heavy enough, maybe you can do that. It's hard. I've been thinking about, I think dark matter above, let's say 10 to the 10 or 10 to 11 GeV could be electrically charged. So I was thinking about how maybe you can look for super heavy dark matter charge 1, but I'm not quite sure how to do that.
I see.
It's definitely harder to look for it.
I see. So then the multi-scattering process, people have studied that. Multiple scattering processes for heavy dark matter. Is there any limit on that?
I don't remember.
I see.
There was this paper. When I read this paper, this is what motivated me to think about heavy dark matter. Let me send it on Zoom.
Okay.
I think maybe this paper.
Oh, I see. So title has multi-scatter events.
Right.
Okay, so I will take a look and okay. Okay, so I guess I think the professors from KIAS, they have already left, but they might have enjoyed your talk much. I should have asked them to say hello, but they left. They have already left. In any case, yeah, I think that we have a pretty good discussion, and I think we have all enjoyed your talk. So
Thank you.
in such an early time, so let's keep in touch. We can keep discussing and then keep collaborating. Yeah.
Of course, I'm happy to discuss if you want the models you're thinking about.
Yeah, sure. I have a draft. I can send you immediately.
Ah, cool.
I have it in somewhere in my computer.
Okay, cool. And I should say I also enjoyed very much the talk. I appreciate all the questions and
so
that you all asked.
Yeah. Do you continue to work with Hyungjin?
So the problem is since